Now, when you're using the sine rule to find an angle, so far we've looked at this version of the rule which had the sides on the top. Now this is the easiest way to use it, put the unknown thing top left. So when you're finding an angle, it's easy to flip this, find the reciprocal of both sides, and start with the angle that you don't know over the side that you do know that's opposite it, and then compare that to the ratio of a different pair. Now there's something we have to consider. When you're finding an angle, you have to consider the ambiguous case of the sine rule. What does that mean? Well, think through when we learnt about all stations to central. We know that sine ratios are positive in the first two quadrants. So that means we need to check when we find an unknown angle. There's two things it could be. It could be acute, but it could actually be obtuse as well. Now we know this because if I do my calculations and I find, say, sine A equals a half, I might say, all right, A must be 30 degrees, but it's possible it could also be the supplement of 30 degrees. It could be 150. Now, how are you going to know whether it could be that large angle or not? Well, check if it's possible by looking at the angle sum of the triangle. All three angles have to add up to 180. So if one of them's 150 and one of the angles you started with was bigger than 30, that won't be possible, and you'll know that there's only one answer. But as we'll see with a couple of examples, you need to check every time because occasionally there will be two answers. So in this example, we need to find theta. Now the first thing to consider is that diagrams may not be drawn to scale. So you can't make assumptions based on what things look like in the picture. All right, so have we got our opposite sides here? Double checking the sides are actually opposite the angles we're interested in. Yes, we've got two pairs. So let's start by writing out the rule that you're going to use. Sine A over A equals sine B over B. Why to write it out? Well, you haven't used it a lot yet, so writing it out every time means that after a while you'll just commit this to memory really easily. Okay, we're finding this one. So let's start with what we don't know. Sine of theta over its opposite side equals the sine of 45 degrees over its opposite side. Now, to get sine theta as the subject here, I need to multiply both sides by 7 root 6. So I can do sine of 45 degrees over 14 times 7 root 6. Now here I can see I've got 7 and 14, so I'm going to simplify this by dividing by 7 and dividing by 7. On the next line, I can also see I've got sine of 45 degrees, and I know that that's an exact one. That's 1 over root 2. So I've got sine of 45 divided by 2. I'm going to just multiply that by a half, okay, and multiply that by root 6. Okay, now root 6 divided by root 2 is square root of 3, and half of that gives me square root of 3 over 2. Now again, I've got an exact value here that I know. I know that the sine of 60 degrees equals root 3 over 2. So I say, all right, theta must be 60 degrees. But I've only found one solution so far. Remember, I need to investigate the obtuse solution. So 180 minus 60 is 120 degrees, and I need to check whether theta might be able to be 120. Now, how do I tell? Well, if 60 is definitely a solution, 120 may or may not be. Now, if theta was 120 degrees, 120 plus 45 gives me 165, which is less than 180. That would leave 15 degrees for the other angle. So it is actually possible, and there are two answers, and I'm going to leave that there as a second solution. Now you might be saying, but it doesn't look right with the picture. Well, perhaps the picture just wasn't to scale. It would be possible to draw a 45 degree angle here and a 120 degree angle here, and have those come up to a 15 degree angle up there. So that would then have 14 and 7 root 6, and this triangle actually does work and could exist. Let's look at one more example. Here I need to find theta again, so I've written my version of the sine rule using the sine of an angle as the first thing that I write down. Now, what I'm looking for is sine theta, so I write that first, and I put it over its opposite side, and then I say that's equal to sine of 80 degrees over its opposite side. Now to get sine theta on its own, I multiply both sides by 11, Now, if I know the sine of theta, to find theta itself, I need to find the inverse sine of both sides. So I write that out. Now, some of you might be tempted to work this out on your calculator first, then do inverse sine of the answer. That's not wrong. I prefer to do it this way because I've shown all my working really clearly. While I've got my pen in my hand, I can do all of the working, and then I just reach for my calculator once and put it all in at one time. So here my answer is 46 degrees and 14 minutes. Now that's just my first answer. I need to consider whether there would be an obtuse answer as well. How do I do that? 180 minus my answer equals 133 degrees and 46 minutes. All right, I need to consider whether or not this is an acceptable answer. If I was to put this here where theta is, then 133 plus 80, I'm already well over the angle sum of the entire triangle. So I can clearly see that this won't exist because there's no degrees left for that third angle. So if I was to try and build this, that 80 degrees and this coming out at 130, these two lines would never join up, and it isn't actually even a triangle. So I've considered this possibility and then I've abandoned it. And that's a perfectly acceptable way to check. Just put it to your drawing and think about it.